So an important way in which the planets, the terrestrial planets, are different are their atmospheres. And as it turns out, the Earth's atmosphere is key to ultimately making Earth livable. So the Earth's atmosphere is important in the ways, the erosive ways we talked about, that Earth's surface has been kind of resurfaced over time. But more importantly, it's number 2 up there, is that the Earth's atmosphere protects us on the Earth's surface from harmful rays from the sun. The Earth's atmosphere is key in making just the right surface temperatures, not too hot, not too cold. And last but not least, the Earth's atmosphere actually during the daytime is what ultimately why our daytime skies look blue. Because if you're on a different planet, the skies won't necessarily look blue in the daytime. So an important aspect of the Earth's atmosphere is that it blocks harmful rays. So some harmful radiation coming from the sun. Kind of what you see from left to right up here are the shortest wavelengths, or the short wavelength X-rays, a little bit longer ultraviolet, a little bit longer visible. And this figure kind of shows you how far down the rays of that sort of radiation from the sun penetrate the Earth's atmosphere. So you can see X-rays are blocked high in the Earth's atmosphere. Ultraviolet get to a certain point. Actually, ultraviolet radiation from the sun is blocked by, you've heard of the ozone layer in our stratosphere. And then visible light, you can see, gets all the way through the Earth's atmosphere. So from shortest wavelength to longest wavelength across the top there. Remember that what will happen when energy interacts with matter depends upon the wavelength of the energy and the type of matter it's interacting with. So as far as trying to gather information in these various regions of energies, now we see gamma rays from left to right, X-rays, ultraviolet, visible, and then longer than visible is infrared and radio. In order to gather information from celestial objects, we need to go ahead and put telescopes beyond Earth's atmosphere. So here you see the Fermi, the Swift, the Chandra, Hubble, Spitzer, and WMAP. These are all telescopes that looked at these various regions of the electromagnetic spectrum, looked at these various energies, and they did so beyond Earth's orbit. So the third thing on a few slides ago said that the Earth's atmosphere keeps us just the right, our surface temperatures on Earth are pretty great for life as we know it anyway. There's something called the greenhouse effect. Now I'm sure you've heard of this before. In fact, you may have heard of the greenhouse effect as kind of being out of control, as being a bad thing, but honestly, the greenhouse effect is important in, if it weren't in place, we would be very cold. The greenhouse effect relies on greenhouse gases. And here in this figure, these little dots here represent greenhouse gases. And what a greenhouse gas will do is, okay, so here we see the yellow light, yellow ray is actually incoming energy from the sun. Specifically, energy that's kind of maybe in the visible region or kind of shorter wavelength region. Notice that as that particular wavelength comes from the sun, it doesn't ping or bounce off of those greenhouse gases. It will actually hit the Earth, and some of that energy will be converted to thermal energy or infrared radiation. Okay, those are the same things. Infrared radiation, part of infrared is thermal energy. So then we see then that the Earth's surface wants to cool off, and that's this little wiggly red thing here. So these little wiggly red things are the Earth trying to cool off. Well, here now we see at that longer wavelength, these greenhouse gases do interact. And so they kind of act as a blanket for that, what we call outgoing thermal radiation, that cooling off of the Earth. So now we have these gases that keep us warmer, and we call these greenhouse gases. And this is the greenhouse effect. And honestly, the culprit you hear in the news as far as being concerned with how our global warming is going on is carbon dioxide, because carbon dioxide is a greenhouse gas, one of the many greenhouse gases, and carbon dioxide is created as we burn fossil fuels. So that's kind of how that goes. So let me go back here. One more thing I wanted to say is there's something called the enhanced greenhouse effect, and that's what we're concerned about. Increasing the amount of carbon dioxide in our atmosphere can take something that we need to be here, the greenhouse effect, and enhance it. All right, greenhouse gases. So greenhouse gas is anything that can absorb infrared. Remember, that's thermal energy. Examples of greenhouse gases, I mentioned carbon dioxide, water vapor, methane. True story, now this has been a few years ago, but as far as being concerned about putting more carbon dioxide in the Earth's atmosphere, there was a concern about putting more methane in the Earth's atmosphere too. And a source of methane is cows. I don't know, they have multiple stomachs and they just produce their fair share of methane. So there was, I don't think it went through, but there was like, well, maybe we should tax farmers who have cows that put methane into the atmosphere. I just thought that was striking. Okay. Other greenhouse gases are oxygen and nitrogen, and I would imagine, in my own mind anyway, I consider nitrogen a less effective greenhouse gas than carbon dioxide. So, as I mentioned, greenhouse gases and the greenhouse effect. Is that a good thing or a bad thing? Well, we need a little bit of that blanket, otherwise surface temperatures will be too cold for life to survive. But when we talk about the planet Venus coming up, we're going to see that Venus's atmosphere is very, very thick, which means it has a lot of molecules per a given volume. And the gas in Venus's atmosphere is mostly carbon dioxide. So actually Venus has an issue with being really, really hot. So we wouldn't want to be as hot as Venus. So one of the last things I want to touch on with regard to the Earth's atmosphere is it's the Earth's atmosphere, specifically nitrogen in the Earth's atmosphere, that kind of gives the Earth's atmosphere in the daytime its blue color. It's what we call Raleigh scattering. And what happens is that incoming light from, I'll just put this whole thing up here. Incoming light from the sun coming in all wavelengths, that would be from the longest wavelength red to the shortest wavelength, Roy G. Biv, to the shortest wavelength violet, all right? Of those colors, blue light is preferentially scattered by nitrogen. And so you kind of picture, and you can kind of see some ping-ponging around. That is blue light coming from the sun, and those little balls there would be nitrogen. And so that kind of scatters that component of light. And so it's that scattering that we see as blue skies. And it's also then that scattering that as the sun is low on the horizon at either sunrise or sunset, when the sun is low on the horizon, that means there's more of the Earth's atmosphere, so we have more scattering and ultimately even removal of those shorter wavelengths of color. So that's why when the sun is low on the horizon, it has kind of this reddish appearance.